Alright, so moving on to the third question here. It's a question on the integral test to determine whether or not a series is convergent or divergent. So let's do a brief review of the integral test. I'm not going to give the proof of the integral test. I'm going to just remind you of this picture. So to use the integral test on a series, you need the terms to, So what we're going to do is connect the sequence with the continuous function, right, by replacing by replacing n with x. We want to look at this function. Let's just do the first one as an example. So let's say I change n to x and I make this continuous function x times e to the minus x. So what you'll find here is that this function is decreasing, continuous, and positive. So these are the conditions that you need to use the integral test. Decreasing, continuous, and positive. Usually these are no problem. And the reason that you need these conditions is because you want a picture that basically looks like this. So something kind of with this concave up and it's going to 0. Alright, and so in this situation what you can do is, if you want to, so there's a way to prove that the integral, so that's the area under this curve after 1, so take the improper integral after 1 of f of x dx, so from 1 to infinity, and then there's a really easy argument that shows that the area under this curve after 1 is finite if and only if this sum adds up to something finite. So just for example, I can make the sum be an overestimate if I draw some boxes like this. Okay, so this is at the integers that these terms, and these are the terms in the series, they agree with the function. So I put in 1, that's the same thing as putting in 1 here. And if I make a bunch of boxes here that have 1 as their base, then the area is just going to be determined by their height. Okay, so what is the height here? The height here is what happens when you plug in 1 is a1. The height here is a2. So what this picture shows is that whatever this improper integral is, it's going to be less than the sum of the series. Okay, and so, and then you could also show that if the integral is finite, then the series is finite if you just draw these boxes the other direction. And so that's an exercise left to you, okay? Alright, so now consider the magenta boxes and convince yourself that if the black area is finite, then the area that represents the sum is finite also. And so in this case it's the magenta boxes. Enough argumentation. Let's just do it. So what we have to do is do the integral of this function. Okay. So let's set it up. We want to look at the integral from 1 to infinity of x times e to the minus x dx, and we're going to let that decide whether or not the series adds up to something finite. And what is this? This is integration by parts. So make u the thing that gets simpler when you take the derivative, and make dv the other thing, dx. Okay, so now I have to do this antiderivative in my head. I should know that it's this. And this I have to do the derivative. So du is equal to dx. Alright, so using the integration by parts formula, which is u dv equals u times v minus the integral of v du. Okay, so plugging everything in here, this is x times minus e to the minus x. And what else? So now I've got minus becomes a plus, e to the minus x dx. Okay, And no, I've lost my limits here, but let's just go ahead and let's take the indefinite integral, and then I'll put the limits in back at the end. So what's going on here, I've got minus x times e to the minus x minus e to the minus x. And then I would say plus c, but so now I can just look at the limits from 1 to infinity. I'm going to pretend like you've done this enough times to know. Well, let's just do it carefully. Okay, so what does this really mean? What you have to do is you have to use some letter like t to stand for infinity. Okay, minus e to the minus x. So let's do from 1 to t. And then what we're supposed to do is take the limit here as t goes to infinity. So what happens as t goes to infinity? So I've got minus t times e to the minus t minus e to the minus t. Okay, minus, now everything becomes positive actually, right? Because both of these terms are negative. So plus t times e to the minus t plus e to the minus t. So what's going on here? It's pretty clear that these two are going to go to 0, right? You should be able to see that, because that's 1 over e to the t, so these things are going to 0. And you have this little, I mean, if you're experienced, then you know these other two go to 0 too. But just to make it clear, let's do, like, let's say this one. Okay, so you know you can look at these piece by piece. These are the ones we have left to worry about. And both of these are just easy L'Hopital's rule questions. Just look at the limit as t goes to infinity. T over e to the minus t is real. Oh, sorry, t over e to the t. This is really what we need to know, right? That's kind of what both of these are. That's going to determine whether these are finite or infinite. So use L'Hopital's rule once. It's the same thing as the limit as t goes to infinity. And on top you get 1, and on the bottom e to the t stays e to the t, and this is 0. So in fact everything goes to 0. Which is a little strange. Shouldn't really be 0, should it? Should I worry about that? Sorry. So here I get the minus and the minus and the minus. Then what happens? Oh, shoot. I'm sorry, I did something really dumb. Let's see if I can fix it. Probably you guys have been like absolutely freaking out, right? Because you knew that I did something dumb a long time ago, but you didn't tell me. You didn't tell me because this is a video. But what I did here, look, when I plugged in the limits, I plugged in t both places, but for these I should have plugged in 1. Right, these should be 1, so sorry about that. But it wasn't completely in vain, because we did show that these two pieces go to 0. So all that was necessary. It's just that this is equal to 1, so this is e to the minus 1 plus e to the minus 1. Okay, and so at any rate, it's finite, right? The point is that the integral converges. So the integral converges, and that means that this sum converges. Doesn't mean that the sum of the series is the same as the area under the curve, but convergence and divergence are the same. Whew. So that one was relatively long. These other ones are easy. So B, you should just know this is the p-test. Okay, so just the p-test for integrals here is inherited by the series, and so let me just remind you that this converges. Should definitely know this if p is greater than 1, and diverges if p is less than or equal to 1. And so, you know, you could just replacing n with x here and using the integral test, you can see that since p is 5, this is the converges case, so B converges. Very well. Okay, and number C is a little bit challenging, but you should be familiar with these two. So just set it up, 1 over x, and now I've got natural log of x squared dx. So how do you do that one, smart guy? It's u substitution with u equals natural log of x. So notice that if you make u natural log of x, then du is sitting right here, right? Okay, so if you do du, then you get 1 over x dx. And so that's the thing in yellow, and so let's forget about the limits for a second. Then we get, this is du over u squared. So it's just du over u squared. Great, and so the integral of that, this is like u to the minus 2, so it's just u to the minus 1 and then plus c, but hold off on the plus c because I'm going to put the limits back in a second. Alright, and so this is minus natural log of x to the minus 1. Okay, and now let's put the limits back. So we've got negative 1 over natural log of x as x goes from 1 to infinity. Alright, so when you plug in infinity, since natural log of x is an increasing function, it's going to be 0, right? Minus what happens when you plug in 1, it diverges, huh? So you've got, what you need to take here is the limit as t goes to 1 of this, you could write minus 1 here, the negatives could cancel. So you've got 1 up there, you've got natural log of t down here. So this is a limit of the form 1 over 0, and so this is actually infinity. Alright, and so this diverges. Okay, so the answer to C is diverges. And what else? Did I? Yeah, okay, fine. You know what? This one is a little bit silly though, because if you start this n at 2, then you don't have that problem. So what we did is right. This is probably a typo. If this n is 2, what happens if that n is 2? Then you can start this integral at 2. Then if you start the integral at 2 down here, you get a 2 here, and then this becomes a 2. And so instead of infinity, which you get in that case is just 1 over natural log of 2, which is a perfectly good number, and in that case it would converge, right? So what's making everything weird, or anyway, so maybe it's good to do it both ways, right? So the infinity here is coming from n equals 1, because actually that gives you 1 over 0 for the very first term, and that's what's causing the infinity. So if I'd written it the right way with the n equals 2 here, then it would have been converges for part C too. Okay, so that's what practice exams are for. And D, let's look at D. So here I've got natural log of n over n cubed. It's too bad that we have to do this with an integral test because, oh wait, this is integration by parts, right? So let's just do it real quick. So we have n equals 1 to infinity, and now n equals 1 causes no problem because natural log is upstairs. You have ln x over x cubed dx. And how do you do it? It's integration by parts. So let u equal natural log of x because u loves natural log of x. So then du is dx, and dv is dx over x cubed. And so that means v is x to the minus 2 divided by minus 2. And what shakes out? Let's see. So use your integration by parts skills, and now you write down natural log of x times, this is u times v. We've got this horrible thing, 1 over negative 2x squared. And now it's just this, right? So I can do plus and cancel this minus. And what I have is dx over x squared. Great. So we've got natural log of x over minus 2 times x squared. And now this part has become minus x to the minus 1. In other words, that. Okay, all right. And I can put the limits in. So the limits are supposed to go from 1 to infinity. Okay. All right. So maybe we should do it the right way, huh? And so let that be t, and then we'll take the limit as t goes to infinity. So what happens when you plug in t? We want to take the limit as t goes to infinity. We have natural log of t over minus 2 times t squared minus 1 over t. Okay, and now I'm not going to repeat my failure from the previous problem. I really am going to plug in 1. So that makes this part 0, because it's 0 over something. And it gives me 1 here, and minus minus is plus, so this is plus 1. Alright. So now, your limit taking skills. The 1 is going to stay the same. This part is going to go to 0. And what's going to happen here, you could do L'Hopital's rule once, and that would convince you that this thing is going to go to 0 because t squared grows so much faster than natural log. Okay, so t squared grows faster than natural log. If you don't believe me, use L'Hopital's rule once. And so this part is 0 too, and so the whole thing is 1, but the point is that it converges. And so the series also converges. And that's the end of this problem.